All right, so let's say that a clay that we've tested is at our site. So we've tested the clay, and we found that SU over sigma prime I is 0.75, and the equation for the drain strength, so for our more failure envelope, is this. For the sake of discussion here, keep our math easy, I'm writing it in equation form. 0.92x plus 1.76. And at our site, this is our t equals 0 minus, it's just a deep clay site. And we are going to build this building at the site. And what we are interested in is what is the strength at our point of interest. So, in other words, we're concerned about a bearing capacity failure, what they call, whereby we get a shear plane underneath our structure, looks like that, and our building essentially tips over, and so we want to analyze what's going on this shear plane, and so we want to know, in this particular case, what's the strength right there, and there's our point of interest. Now, we're interested in other points as well, but for this problem, we're just going to do that point. And it ends up, of course, we find that the strength over here is different from the strength there, is different from the strength there. So this is why we have to, while we're choosing a point, we're going to find the strength at that particular point. And some details of our structure, 10 meters. The surface stress is 100 kilopascals. And what we want to do is we want to find our tau FF, both drained and undrained, at that particular point of interest, given the test results that we've already obtained. So we have our unit weight of that clay, we have the water table there, and what we want to do, so what we're going to do is we're going to begin by getting sigma prime I from this soil profile. So in other words, our t equals 0 minus gives us our sigma prime I. So before the structure is put down. Now, we're going to make the assumption that this building is constructed instantaneously, which of course we can't do, but we are going to, that means what? If it's a rapid loading, so rapid, fast loading, total undrained fast, and so we're interested in the undrained shear strength because total undrained fast. We're interested in undrained shear strength. Of course, this building, we're going to assume that the building is there for 50 years. So we're also going to be interested in the drained shear strength because after 50 years, we're going to assume that the excess pore pressures have dissipated. So, okay, so this is this, and here is that's the Q from our structure. That's the surface stress from our structure, and then we have tau FFs all along that shear surface, and so they're all different, but that is, ideally we would want the shear strengths all along that shear surface in order to do this analysis. And one way of doing it is to take moments about this point, and so this is the moment that will cause shear failure, and the moment caused by these taus resists the shear failure. So one way to do these analyses is to simply take moments caused by the tau FFs and take moments caused by the Q, and make sure that the tau FF is significantly bigger than the moment caused by the Q. So, okay, so to get our SU, Well, we're going to use this sigma prime I and multiply it times our ratio, for instance. So our SU over sigma prime I, which we've determined from our lab tests. So in a straightforward manner, we can get our SU. Okay, so this is the situation at t equals infinity. So at t equals infinity, which, like I say, it could be 50 years or something like that, then we have uxs equaling 0. And then to get our tau ffs, we need to use the c prime and phi prime. So at t equals infinity, we're going to use c prime and phi prime. So, but at t equals 0 plus, so in other words, at t equals 0 plus, we're going to use our SU to get the tau ff. So, all right, so what's the solution to this problem? So we've got both an undrained situation and a drained situation. Well, how do we do the undrained? Well, the undrained is pretty straightforward. We simply look at our t equals 0 plus picture, or, well, sorry, take that back. We look at our t equals 0 minus picture to get our sigma prime I, and that is simply, there's no building there. So we go 10 times 19.8 minus 10 times 9.8. If you look at that, you can go back to the location where we showed the soil profile, and we get 100 for our sigma prime I, and then we simply do what? We simply take the given ratio of 0.75 times the 100, and we get that SU is equal to 75 kilopascals. And we use that, in other words, we use that at our analysis at t equals 0 plus, where we have our building, and we use that tau ff. We use that tau ff in our undrained analysis, taking moments about the point that I indicated. For the drain situation, well, then we're going to look at the building is going to change our effective stress. So we are going to look at our pressure bulbs. I'm not going to go through this in detail. For the point that we're interested in, we have ZF over B equals 1, and it's below the edge. So that's what we're looking at. And if we do that, we go into our pressure bulbs, we get 0.25 as our pressure bulb factor. And so our Q is 100 kilopascals, and that means that at the point that we're interested in, our stress increase is 25 kilopascals because it's deep in the ground. So in other words, this is the surface stress, this is the stress at 10 meters down at the edge, below the edge. And so when we compute what our sigma prime at the point of interest is at t equals infinity, so okay, remember we're assuming t equals infinity, all the excess pore pressure is dissipated, we get this 100 from the sigma prime I, that's that. The delta sigma V, which is the this 25, and we get 125 there. So, and then to get our tau ff, which is the 0.92x plus 1.76, we put in the 125, and we get a tau ff of 117. What is that? Graphically, what are we doing? Here's our failure envelope, and we are at 125, and I just want to know what is that value of tau here. There's my tau ff. So, and of course, this equation is for, or rather, I guess it's the, this equation is for that line. So by just plugging into that expression, I've been able to get my tau FF. So I get 117. And so we use so what does this say? I use tau FF equals 117 for our drained analysis. And I use the 75, tau FF equals 75 for our undrained analysis. We got to do both analyses. So a lot of work just to get that, tau FF, that strength, but that's what needs to be done. Okay, so a simpler problem here, but let's look at this one. Let's say I do two drained tests, slow tests. Okay, we're effective, drained, slow. So we're slow test to drain test to slow test. No excess pore pressures generated, and these are the results of these drain tests. And notice that I only have, your stress strain type curve. I don't have any excess pore pressure curve because the excess pore pressures are zero because it's a drain test. And very simply find C prime and phi prime. So I have my cross-sectional area here is 0.09 square meters. This is F, so I have to take, and this is P, so I have to go F over A cross and P over A cross. So these two numbers go together, and these two numbers go together. So I have the 3.15 here. I have the 3.08 here. Divide both of them by the cross-sectional area. And then I have the 5.5 there. I have the 4.2 there. And I get, both my sigma prime and my taus. And then I simply now there's my x, there's my y, there's my x, there's my y. I plot those points. I get these 2 points, and then we do the usual, which is, I'm not going to go through this, get the slope, delta y over delta x. I then, get the intercept using, our standard procedures. So I get my expression for this line now, and then we know that the intercept B is the C prime, and the arctangent of the slope is the phi prime, which is 25 degrees. So two drain tests, pretty easy to get the C prime and phi prime. Okay, typical quiz that I'll give you, I give you the curves, the test results. The raw test results are these stress strain curves. And then you need to calculate the C prime, the phi prime, the SU over sigma prime I. I'll give you enough information to get both of those in most cases. Most students can do this quite well. Strangely enough, the second part is more difficult. Getting the tau FF in situ, or people find it more difficult. It's not difficult. But this is the important part, in a way, to get the tau FF in situ. The whole reason that we go through the testing and get these parameters is it so that we know the strength in situ. So you need to be able to get both the drained and undrained tau FF in situ. In other words, study both parts of this because you need to be able to do both of them. Okay, I want to say one other thing about this. We said that the SU over sigma prime I is a constant, but, well, it is a constant within a certain OCR within a certain overconsolidation ratio. So in other words, if I plot up OCR on the x-axis and SU over sigma prime I on the y-axis, then we find that we get a little bit of a curve, but straight line at times can represent it. So for instance, if I have bay mud, typical numbers are we get an OCR of 1.0, normally consolidated bay mud. I get approximately an SU over sigma prime I of about 0.35. At 1.4 OCR, I get about 0.41. So these numbers are handy to know for at least to make an estimate. Now, of course, this is not everywhere. You have to test the soil yourself, but these are typical numbers that you'll find. And so if you have for instance, this bay mud soil profile, and it's normally consolidated, for instance, and we want to know, for instance, what is the undrained shear strength, the tau FF, or SU, at a depth of 4 feet, then it's pretty straightforward. You can at least make an estimate before you do anything, knowing the approximate density. We can simply get our sigma prime I. Well, at 4 is 4 times 100 minus 4 times 62.4 with the water table at the ground surface. And we get a sigma prime I of 150. Well, if I know this, if I'm using this 0.35, then I simply go 0.35 times 150 gives me my SU, 53 PSF. We don't even do any tests. We just simply use this number, which is a common number. Now, of course, you wouldn't use this for any sort of final design or anything like that, but it gives you a ballpark number to get started with, whatever evaluations you need to do. So once you have that SU over sigma prime I, you can do a lot with it. Okay, so another problem that would be similar to a quiz. This is getting closer to the layout of the quizzes I'm going to give you. I would give you a soil profile, looks like this. And I give you a bunch of locations where samples have been taken. So I've got A, B, C, D, and E, and if you notice, I've got sand, I've got clay, I've got sand, and we've determined the in situ OCR of this clay to be 1.2. Here are all the densities of these soils, and then the direct shear tests were run, and these are my curves for each sample. So for this sample I got this result. For B, I got this result. For C, I got that result. For D, I got that result. And for E, in the sand, I got that result. So that's the way these match up. So we did one test on each sample, which is, and I'm going to note that all the stresses are in kilopascals, and if no UXS is given, it was not measured in the test. Okay, all the tests are all direct shear tests, and what we want to do is we want to find in the clay C prime and Phi prime, and we want to get the undrained shear strength at 9 meters in situ. So notice there's no test at 9 meters, so that's one thing. And but we want to be able to estimate the strength there using this data. And then in the sand, we want the Phi prime. So I've labeled the peaks here, so you get peak values. You don't have to pick them off yourself, typically. Here, there is the excess pore pressure at failure. Now notice each test is labeled. So this is a slow test. Fast, fast, fast. Well, what does that tell you? That tells you that this is a drain test because it's slow. Effective drain slow, EDS. This is fast, total undrained fast. So this is an undrained test, undrained test, undrained test. And this is slow, it's in the sand. Notice this is in the sand. So it's a drain test in the sand, which is what we're always going to have. So you have to pay attention to, if this is the drain test, I can't get my undrained strength from a drain test. And notice no excess pore pressure was measured for that one. For these two that are fast, if it's slow, we know the excess pore pressure is 0. The excess pore pressure is 0 with those for the slow ones. But so, all right, how do we handle this now that we've done it? Well, we're going to fill out this table, and this is going to be in the instructions. So here's our samples, A, B, C, D, and E. And we note that these are in the clay, this one's in the sand. And we simply get that by looking at the soil profile. Now, I should say, and how do I get our sigma prime in situ? Well, that I look at the soil profile and I get my sigma prime in situ. I'm not going to do that calculation because you can all do this at this point. You just look at the soil profile and calculate. These numbers are the effective stresses in the ground for the soil profile shown. Now I want to get what is my sigma prime P in situ. In other words, what is the greatest stress that the soil at that location has felt? And what do? Well, I've given you the OCR in situ, and the OCR in situ that I gave you is 1.2. So what do? I simply, 1.2 times 54.4, 65.3. 1.2 times 74.8 is 89.8. So, and the sand, of course, doesn't have an OCR, so we're not going to put it in there. So I get my sigma prime P in situ. And then how do I get, I'm going to look at the sigma prime I of the sample. What's the sigma prime I of the sample? Those are given also. Those are given. How do I get those? 70, 30, 19, 17, 200. Where do those come from? I gave it to you. 70, 30, 19, 17, 200. So those are the sigma prime I's. In other words, those are what we consolidated these samples to during the consolidation phase. And then, so this is what the sample felt. Well, what is the sigma prime P of the sample? What does that mean? That means sigma prime P of the sample, what is the greatest effective stress that the sample has ever felt? Well, how do I get this? Well, if I look here, well, in the ground, that particular sample or point or whatever felt 65.3, but in the lab we put on 70. So that means that, the greatest it's ever felt is 70. So I put 70 here. It's the greatest. Now, so in other words, I'm at column 5. The column 5 is the greater of columns 3 and column 4. So I compare column 3, I compare column 4. The biggest one gives me column 5. So in other words, 89.8, 30, well, 89.8 is the greatest it's ever felt. Because it felt 89.8 in the ground, we only put 30 in the lab. The same thing, 114, 19, 114 is the greatest. 139, 17, 139 is the greatest. So what we've put on in the lab, well, for these last 3, is less than what it felt in situ. So the in situ stresses are the ones that represent the greatest stress on that sample. Now here's the thing. That means that we have what's called an OCR for our sample. Now remember what the definition of OCR is. It's sigma prime OCR is sigma prime P over sigma prime I. So, and we're talking about the sample here. So here's my sigma prime I of my sample. So what's my OCR of my sample? Well, it's going to be sigma prime P of the sample divided by sigma prime I of the sample. So in other words, column 5 over column 4 gives me column 6. So column 5 over column 4 gives me column 6. So the OCR of the sample, 70 over 70, that's 1. 89.8 over 30 is 2.99. So what's happened here, so 114 over 19, well, that's 6. And so 139 over 17. Now whether it's is 8.2. So whether it's deliberate or not, notice that I've created samples that have different OCRs. Sometimes you can do it on purpose, sometimes you don't. But in any event, what happens is you've got to work with the data that you have, and sometimes you're working with somebody else's data. And it may not be perfect, but you need to figure out, okay, what's going on with my sample. So I have a bunch of different OCRs for my samples now, by accident or deliberately. Okay, so now, again, for column 8 here, these are given in the test. So that's the tau FFs of the test, 32, 15.9, for instance. That's our 32, 15.9, 16.5, 20.4, 81. So that's given, all those tau FFs. And there they are. And then I look at the test type. Well, if they're slow, I look at the speed of the test. Is it fast? Is it slow? If it's slow, it's drained. If it's slow, it's drained. And then if it's fast, then these are undrained. So those are undrained. And then I want to get my SU. So, well, I can't get an SU from a drain test, so I don't have anything there. But if it's an undrained test, then what? My SU. So if these are undrained, then my SU is the same as my tau FF. So I've got my SUs here. And the next column is SU over sigma prime I. Well, there's my sigma prime I is column 4. My SU is column 10. So column 10 over column 4 gives me column 11. So 10 over 4. I just divide those out. Now, and then my sigma prime FF, well, what's that going to be? Well, again, I look at my sigma prime I of my sample minus my UXS. Well, okay, so what's my UXS? Well, if I have a drain test, my UXS is 0. So those are easy. But if I have an undrained test, I have 3 undrained tests here. Well, did I measure the excess pore pressure? Well, it ends up that I only measured the excess pore pressure in this one, and that was 8. So I'm going to have my sigma prime I, which I got the 30 minus the 8, so 30 minus 8, I get 22 for that one. All the other ones, I don't know what they are because I didn't measure them. So, whoops. 19 minus question mark. I don't know what those are, so I leave those blank. But I do have the sigma prime FF for these 3 tests. And then, so with all that information, now I can plot these up. So I'll do the sand first because the sand's pretty straightforward. I take the 281 for the sand because that's over here, 281. I plot that up. So 281. I know it goes through the origin, so I draw a line that looks like that. And the arctangent of the slope, y over x, 81 over 200, gives me my friction angle for the sand is 22 degrees. All stresses here are in kilopascals. So what do? I need 2 points to plot my failure envelope for my clay drained. And so, I have to use, these are the only 2 that I have because, these are, I don't know what they are. So I have to use those 2. So I'm taking those sigmas and those taus. I put them here. I'm not going to go through this again, but once we've got these 2 points, I can draw that line. I get the slope. I get, the intercept. So I get my phi prime and I get my c prime for that. Now I need to plot SU over sigma prime I versus OCR. So remember we had many different OCRs for our tests, and I pointed them out. So in other words, on the x-axis is OCR, on the y-axis is SU over sigma prime I. So if we go back to our results, we have our different OCRs, and we have our here it is, SU over sigma prime I here. So we can't use the top one because that's a drain test. So we just use the undrained test here. And so we're using, these points. That's my x-axis, 2.9968.2. My y-axis number is 0.53, 0.87, 1.2. So I plot those up. And I get how SU over sigma prime I varies with OCR. So I plot these. So these are the 3 points from our 3 undrained tests. And you can look at this. They're all plotted approximately. And then, now, here's the thing. Notice that my OCR is 3, 6, 8.2. And what is my OCR in situ? So the OCR in situ is only 1.2. So got a little problem here in a sense, because now I need to, I sort of get a line here. I'm going to call it, it's not a straight line, but what I'm going to do is I'm going to work with these last 2 points and extend this backwards so I can get to, 1.2 on the OCR. That's my goal. I don't want to use these 2 points because they're too far away. But I'm just going to take these 2 points, and I'm going to assume it's a straight line from there to there. And so again, I'm going to write an equation for that straight line. I'm not going to go through it. There's my delta y over delta x, y equals mx plus b. So I create an equation for this line. I'm going to extend it for my OCR equals 1.2. So here's the equation of that line. I'm now going to put in an OCR of 1.2 for the x, and I get an SU or sigma prime I of 0.327 for my in situ OCR. And then what do I want? Well, I want to get, if I get my sigma prime I at 9 meters in situ, then I can get my SU. So this is my sigma. Look at the soil profile. You can get that. That is my sigma prime I at my in situ. For the soil profile, I get the sigma prime I in situ, which is 105.4. And then I simply take my SU or sigma prime I, 0.327, times the 105.4. And I get 34.5 kilopascals. So a lot of work to get what is the strength in situ at 9 meters from all those tests. But that's what needs to be done. And let me just say, yeah, you need to know how to do this, okay? So a little bit tricky, but overall straightforward once you understand what's going on here. So let's get that page. Okay, I will stop.